for ion making purpose, I think the reactor has to be much larger because we have to produce from the same facility. We have to produce a lot more iron. Copper is a lot more expensive per unit weight than iron.
Yes, sir.
Yeah, I was just wondering, a question about the process. You're trying to eliminate the use of pelletization, which is reducing the ore down, I'm assuming, to a smaller particle to go into the furnace. In the new technology, is it still, though not called pelletization, is it some other kind of reduction of an even smaller particle so that it can get this more instantaneous reaction?
I do not envision the need for that because the concentrate particles that we produce in this country currently are fine, sufficiently fine at about 30 micrometer size. Another thing is to reduce the size even further. The already small particles requires additional energy. Currently at this time, such fine concentrate are already being produced, even to use in blast furnace. They're already used. So,
I missed that. I'm sorry. Thank
right.
Okay, it's a good question. Dana?
The timing again, we're all often asked in terms of if everything went the right way, how long to get this technology into the field. And I think Andy was asked that at Senate EPW committee hearing. And so your response, if everything goes right, would be how many years? 10 to 15?
That will be as I showed in the last slide. Oh, sorry, I'm going wrong. Okay, about 3 years phase 2 work, and then 4 years, maybe 4 years after that, maybe a little too optimistic, but certainly by 7 years through the phase 3 for industrial pilot plant test. So the production scale, which can actually be a substantial part of the actual production, may, if everything goes well, may start in about 10 years. 10 years. So that's our optimistic hope, if everything goes well.
That would be for the first one day. I mean, obviously, by the time you get to the first ton, 10, 11-year time frame, if ever, is certainly within the earliest it could happen to get the first one. Yeah, it's a reasonable range.
That's the number we use, yeah.
Yeah.
And
Yeah.
You would say that's generally true with the other CO2 breakthrough projects?
Yes.
Like molten
Yes.
oxide
Molten
electrolysis?
oxide electrolysis. The only one that's a little more nearer term is the sequestration project at Missouri University of Science and Technology, which might be 5-6 years, because most of the background technology exists for that.
Yeah. Scott?
To that point, though, I mean, 10 years before you got this industrial pilot size done, what's the difference between going from 100,000 tons per year to, I mean, I think about even 1 or 2 of our plants where we're talking 2 or 3 million tons a year out of one current facility.
Mm-hmm.
There's a big gap between 100,000 tons a year and 2 or 3, which is actually a pretty small facility. What's involved in ramping that to, I mean, what would you see as the business model? Lots of small furnaces like this, or large scale facilities that do 2 or 3 million tons a year?
In my opinion, we have to go with a very large, not large number of mid-sized reactors and so on. I believe we have to go to a very large reactors to keep the economy of size and so on. And during that development process, I see the burner development as one of the key aspects of the testing as well, development as well as testing.
Just a little more on that. Once, you get something out of a pilot scale to go to a demonstration or part commercial scale, a scale up of 10 to 1 is typical. So if it works at 100,000, the next logical step is at 1 million. And what's happened with these iron making technologies that are coming out now, they're in that 1 million range, and then as they get operational experience, they go 1.2 million, 1.4 million, and that's about a 1-for-1 replacement with a small blast furnace. And most of the steel plant concepts for the future are where you're replacing a really big blast furnace, like Gary 14. It's 2 units side by side. But if the reaction intensity, which Dr. Stone talked about extensively, is such, you take it to its logical single unit size. We don't know what that is. We're hoping it's somewhere north of 1 million tons per year. Does that help?
If I may add a little bit from the experience that copper flash smelters have had. Because although we're dealing with solids, when you inject these particles with gas, they almost behave like gas flow. So where I'm getting at is the scale up is easier when you deal with gas flow, gaseous reactants, and so on, than when you deal with a lot of either condensed phase, solid, or even liquids.
One of the things we consider when you look at adopting new technologies, if it's 10 to 12 years to get the first proven commercial unit, that puts us at the 2018, 2020 timeframe. And then we have a lot of history in the steel industry about bringing in new technologies since our industry has been around for such a long time. Continuous casting, oxygen steelmaking, from the first installation, from the first unit to when a technology was pervasive in the industry, 70–75% deployed, takes 30 years. So, if you're talking about starting it in 2018, 2020, you get out to 2050 timeframe pretty quickly for a new technology to take over. So these are the kind of things we have to consider, not only as businessmen in the steel industry, but when determining policy.
Additional questions? Just a brief comment. Our focus here today is really technology, because at the end of the day, the American steel industry understands that the only ultimate solution to climate change is a technology solution. And I think it's important, as we look at policy alternatives, that we make sure that mandates are coordinated with the pace of technology innovation. It's critical. If one outpaces the other, frankly, it's not going to work. I think sometimes there's just the assumption that if you put mandates out there, that there'll be this great burst of entrepreneurial activity and somehow the new technology will emerge. And I think our point is here today that this industry without mandates understands where we have to get to. And we're investing money and we're running as hard as we can run to get there. But I think you can see what some of the time frames are, because you're really talking about a quantum leap here. This is a whole new paradigm in terms of how you make steel. And I think the very thought 5 or 10 years ago that we'd be talking about making steel without generating CO2 wouldn't have even been on the radar screen. But we understand what's coming. We understand the importance of getting there. And it's not just a U.S. effort, it's a global effort on the part of this industry. And we happen to be sort of carrying the ball on the CO2 breakthrough technologies here in North America. Larry, whether you want to add anything about some of the other technologies we're looking at too, but we've got a couple of others underway as well.
Sure. The other two really promising technologies we have underway, one is called molten oxide electrolysis. That project's at MIT, and that basically uses electricity to separate iron and oxygen. And so you get 2 byproducts when you make iron that way. You get molten iron and you get oxygen. You don't get CO2. That technology has a real chance of being successful, especially as our electricity grid in the U.S. gets greener. And I recently read some good news from the Nuclear Energy Institute, courtesy of Jennifer, the other day, and they're forecasting that if the next installation of nuclear plants here in the U.S. are successful, that by 2035, our electricity grid will be 50% nuclear.